To give you an overview of our session, I will be examining the manufacturing life cycle of the three vital industrial products. Each of the topic I will break down into a few subtopics, that is raw materials, the specific chemical reaction involved, the manufacturing steps, and the co-engineering principle behind them. Let's begin with our first topic, that is the production of the natural rubber glove from the natural latex. Natural rubber products start their life as a milky fluid called Heveva brasiliensis latex, which is collected by tapping the bark of rubber trees. This material is indispensable across the globe, primarily serving as personal protective equipment (PPE) in the healthcare, food processing, and chemical laboratories to prevent contamination. Notably, Malaysia stands as the world's largest production that supplies over 60% of the global demand for the rubber glove. Moving on to our second category, that is the building paint. Paint is a complex chemical formulation consisting of the pigments, binders, solvent, and performance additive. Beyond aesthetics, its primary industrial purpose is as protection, shielding the infrastructure from harsh weather, UV rays, moisture, and corrosion. This makes paint manufacturing a multi-billion-dollar global market, fueled heavily by local and international construction. Lastly, let's look at the PET plastic bottles. PET is a lightweight semi-crystalline thermoplastic polyester materials. It is first developed in the 1940 by Whitfield and Dixon. The PET bottle we know today was invented in 1973 by DuPont engineer Nathaniel White. Because of its exceptional barrier properties, it is being virtually shatterproof, chemically inert, and drastically reducing product loss. It also commands roughly 80% of the entire global PET demand. In Malaysia, this sector is a massive economic driver as supported by the Malaysia Plastic Manufacturers Association. The raw natural rubber latex by itself cannot form a stable commercial product. It requires a heavy chemical modification. The manufacturing matrix relies on a complex cocktail of specialized raw materials that each performing a distinct chemical or mechanical function. For an example, the natural latex is served as the primary base structural material, providing the long flexible carbon backbones that require to form the raw elastic glove film. And then calcium nitrate. This is a highly soluble mineral salt. Its industrial role is to act as a powerful latex collagen. When discussed in solution, the divalent calcium ions interact with the emulsion to instantly solidify a uniform layer of the latex into the hand-shaped molds. Next, the calcium carbonate. This inorganic powder is insoluble in water and is suspended in the collagen bed. It deposits into the mold surface to act as a highly effective physical foamer release agent that ensure the finished rubber glove can be peeled away cleanly at the end of the line without tearing it. Next is the sulfur. This element has a unique ring or chain structure. The function of it is as the primary vulcanization agent. When under a high heat, it will break apart to mix intimately with the polyisoprene particles that create the covalent crosslinks that permanently cure, harden, and lock the polymer network into place. Next is zinc oxide. This is a vital metallic oxide that serves as a compounding activator. It interacts chemically with accelerator to maximize the efficiency of the sulfur cross-linking reaction. Example of the accelerator is like ZDEC or known as zinc diethyl dithiocarbamate. These are organosulfur complex. They drastically speed up the chemical reaction kinetics between the sulfur and the rubber chain during the maturation and curing stages that allow the commercial lines to run at fast variable speeds. Next, the antioxidant. For example, hinder phenolic derivative. These special molecules are incorporated to sacrifice themselves chemically, scavenging free radical to protect the finished glove from thermo-oxidative degradation, ozone cracking, and premature aging over time. Next is the stabilizer and dewebbing agents like the surfactant or soap-based compounds. These surface active molecules stabilize the liquid latex colloid during its 24 to 36-hour chemical maturation tank phase. They also reduce surface tension to prevent thin defective rubber webs from forming between the finger channels of the hand molds. Lastly, the pigment example of it is organic and inorganic colorants. It is added in precise part per 100 rubber ratio to provide the specific aesthetic color or tint, like a medical blue or green, to the final glove. At a molecular level, natural rubber is classified as polyisoprene, a high molecular weight polymer composed of thousands of fleeting hydrocarbon monomer subunits. While the simple isolated monomer is known as 2-methyl-butadiene or isoprene, the biological pathway within the Hevia brasiliensis tree synthesizes this macromolecule using two active precursors, that is isopentyl pyrophosphate and dimethyl allyl pyrophosphate. An essential concept in industrial organic chemistry is stereoisomerism, as the geometric arrangement of a polymer backbone completely dictates its physical behavior. Polyisoprene exists in four distinct structural isomers. Industrial natural rubber is exclusively this 1,4-polyisoprene isomer. In this configuration, the butyl methyl group and the hydrogen atoms sit on the exact same side of the carbon-carbon double bond backbone. This specific special geometry creates a highly flexible coil macromolecular chain with intermolecular forces. This structural layout gives natural rubber its signature high elasticity, tensile strength, and remarkable elongation and great properties. In contrast, the trans one for isomorph a rigid, highly crystalline material known as gutta percha, which behave like a tough plastic rather than an elastic rubber. Next, the raw materials of the building pane. Pane formation does not rely on a single polymer, but rather a carefully calculated suspension containing four core components, that is, the pigment and fillers, binders and resins, solvent, and performance additive. For the pigments and filler, like titanium dioxide, for brilliant white opacity, zinc oxide for built-in antimicrobial protection, and calcium carbonate to give the paint body. Next is the binder and resins, which are organic polymers such as acrylics, alkydes, or epoxies that act as a continuous matrix film to wrap the pigment and glue it to the wall. Next is solvent. Solvent act as volatile carrier fluids, such as water for eco-friendly emulsion paint or petroleum distillates for heavy-duty or base gloss stains to lower the fluid's viscosity for easy application. Lastly, the performance additives like hydroxyl ethyl cellulose, which manipulate the rheology and preventing the paint from splattering or running off the brush. Meat PET bottles. It is built through a step growth polymerization. Its structure relies on two primary petrochemical monomers. That is, the upstream piscine from crude oil is oxidized into purified terephthalic acid, or known as PTA. Meanwhile, ethylene gas is catalytically processed into monoethylene glycol, known as MEG. When, when two of these is mixed together, the PDA provides the rigid aromatic ring for structural stiffness and gas barrier protection, while MEG adds the flexible linkage to all stretching. Accelerated by an antimony catalyst, it creates the crystal clear plastic we rely on nowadays. Now, let's step inside into the non-stop mechanical masterpiece of modern glove manufacturing. Thousands of ceramic formers ride in endless conveyor through strict chemical and thermal zones. First, the raw natural latex is filtered, compound, and matured. The formers are coated in a precise chemical coagulant bed, air dry, and then dipped directly into the liquid latex compound. Next, they enter high temperature vulcanization oven to bake in structural strength, followed by turbulent hot water, leaching, tank to extract water soluble proteins and chemical residues. After a final oven dry, the glove undergo automated inflation and defect testing before being rapidly baked, continuously automated, and strictly controlled from start to finish. Next is the building pane. The flow moves sequentially through a raw material preparation and waiting, shifting into a high shear pigment dispersion that enter intense mechanical grinding and milling, proceeding to the massive letdown and tining process that move to the additive incorporation, that transferred through strict analytical quality checks and being finalized at the high-value automated canning and packaging filling machines. Now, let's down the exact mechanical action and chemical mechanism taking place within each of these. With a precision measurement under ambient condition, the dry pigments, liquid binder, and solvents are meticulously weighted. The raw pigments like titanium dioxide naturally cling together into large air-trapping clusters called agglomerates. To break them apart, they will enter a high-speed dispenser. Each is specialized machine that have a jack-tooth impeller spin at 1500 rpm that generates an intense mechanical vortex. This results a high fluid shear forces strip away trapped air, allowing wetting sufficient to thoroughly coat every single particle that create a thick uniform paste. To achieve true commercial quality, this paste must undergo intense milling. It is pumped into a beef mill packed with ultra-hot zirconium silicate bits. As an internal rotor spins, these microbits smash directly into the paste, crushing the pigments cluster down to microscopic size, often under 20 micrometers. Because this relentless friction generates immense thermal energy, integrated cooling jackets must continuously circulate cold water around the mill. This helps to keep the internal slurry temperature well below 50 degrees Celsius that prevent the binder resin from overheating and gelling prematurely inside the equipment. Once pulverized, the concentrated paste undergoes the let-down process. Transferred to a massive blending tank, it is thinned out with the remaining bulk volume of binder resin and solvent. Large low-speed pedal street gently blend the mixture to avoid creating structural foam. Next come additive incorporation. Biocides are introduced to prevent microbial growth, deformers to pop surface bubbles, and rheology modifier to engineer that perfect non-drip texture. Before leaving the plant, the pet faces rigorously quality control. Technicians utilize viscometers to verify flow-resistant drawdown cuts to test opacity and high-precision spectrophotometers to guarantee an exact color match. Once approved, the pen is filler and sent automated filling lines for cleaning and lastly for baking. Now, let us shift to our focus to the critical area of industrial safety and environmental management. Across all the three manufacturing sectors, workers face highly distinct and intense physical and chemical hazards on a daily basis. For an example, in the natural rubber glove industry, in the glove industry, the primary threats stem from severe thermal risk. Workers operate around large multi-zone continuous curing and drying ovens that run at intense temperature between 100 until 140 degrees Celsius. Furthermore, chemical exposure is a major hazard. By handling the raw vulcanization accelerators, caustic alkalis for mold washing, and corrosive chlorine gas during the powder-free surface treatment stage that require a strict control protocols. Secondly, if we look at the building pen manufacturing, the danger profits shift from thermal to respiratory and chemical. Here, the biggest occupational concern is the inhalation hazard. Workers loading pyrochemical powders such as titanium dioxide or crystalline silica fillers that face a long-term respiratory risk if the dust isn't managed well. Additionally, for the solvent-based paint lines, the volatile organic solvent vapors present severe fire and explosive atmosphere risk. Finally, in PET plastic bottle plants, the environment is dominated by high-pressure pneumatic system and molten materials. Workers face extreme physical safety hazard from stretch blow molding machinery operating at massive pressure of 30 to 40 bar. They also work alongside heavy plastic extruder processing molten polyester resins at temperatures scaling past 250 degrees Celsius that make the severe thermal contact burn a constant risk. Now, let's go to the waste management and the pollution control measure. To mitigate these heavy industrial footprints, modern plants must employ highly specialized waste management and pollution control engineering. The rubber glove manufacturing is notoriously water intensive. The leaching stage strips out excess water-soluble latex proteins by processing the surfactants and residual chemical salts, creating a massive volume of highly acidic and alkaline wastewater. To handle this, factories must run dedicated multi-stage on-site treatment plants. They utilize advanced biological activated sludge system to aggressively neutralize the pH and degraded organic components, dropping the biochemical oxygen demands or BOD to safe legal standards before environmental discharge. In the paint industry, waste management focuses on the liquid containment. Washing out massive blending tanks between color batch generates hazardous wash water packed with pigments, binders, and chemical additives. Paint plants utilize a chemical collagens and flocculation system right on site. By adding specific polymers that bind the liquid chemical waste together that allow them to separate the clean water from a dense toxic paint sludge, which is then dewatered, dry, and safely disposed. Finally, for the PET bottle manufacturing, pollution control looks very different because it is a clean, dry process, but it generates a solid thermoplastic waste. Plants management this by capturing all post-industrial trimmings, defective preforms, and flash scraps. This scrap material is fed directly into high-speed granulators to be repelletized and cleanly blended right back into the production loop, that preventing the scrap plastic from hitting industrial waste streams. Finally, for the sustainability and also the green chemistry initiative, sustainability is no longer optional, but it is actively transforming this field through green chemistry and circular economy principles. In Malaysia, rubber glove sector forward-thinking manufacturers are tackling the heavy carbon footprints by shifting away from fossil fuels. They are installing highly efficient agricultural biomass boilers that burns local palm, kernel shells, or wood chips to generate the massive steam energy that was needed for the drying lines. For the architectural paint industry is executing its green initiative through a profound structural shift in product. Manufacturers are aggressively phasing out traditional oil-based solvent, coating and replacing them with a high-performance water-based acrylic emulsion. This single shift effectively eliminates volatile organic compounds or VOC, drastically reducing the chemical vapors that damage our atmospheric ozone and compromise indoor air quality. Lastly, the PET bottle sector is driving sustainability through the structural engineering and the circular economy. Plants are investing heavily in down-gouging technology, which uses advanced polymer distribution to create ultra-lightweight bottles that use significantly less raw plastic resin while maintaining the structural strength of the PET bottles. Furthermore, the industry is scaling up the integration of the rPET, or known as recycled polyethylene terephthalate, that closing the loop on plastic packaging waste completely. To bring our presentation to a conclusion, let us review the core technical and economic takeaways from today. I mapped the precious industrial life cycle based on the three topics. First, the natural elastomers in rubber glove. Next, the complex chemical colloids in building paints. And lastly, the synthetic polyester in PET plastic bottles. I also observed how minor chemical modifications, such as an ammonia injection to manipulate emulsion pH, a sulfur cross-link to build elastic memory, or precise resin drying to completely prevent a destructive hydrolysis reaction, ultimately dictated the physical properties of the final product. From an industrial standpoint, this system reflects the core tenets of OPT. They illustrate exactly how chemical engineers scale up microscopic chemical reactions out of small laboratory glass flasks and integrate them into massive high-pressure thermally controlled unit operation. By balancing the raw material inputs, thermodynamics laws, processing pressure, and sustainable waste management, this process effectively transform agricultural and petrochemical feedstocks into high-value consumer goods that power a global economy. That's all from me. Thank you.